Now the purpose of this lecture here is to understand why liquid helium can behave as a superfluid. To understand how a superfluid fluid is possible, how it works. Now we start with the approach taken by Landau. Okay. The name is Landau, Lev Landau, a Russian. His idea is to think in terms of the energy loss when, say, a body moves through superfluid helium. So imagine that there's a body of mass m, can be a ball, and around it is the superfluid. And we want to think about what happens when it moves through it, how it might or might not experience resistance. Now as it moves through the liquid, if we suppose that it experiences resistance, that must mean that the body loses energy. Now if it loses energy, somehow, okay, the energy goes to the liquid and it must show itself in liquid in some form of thermal energy or some form of vibrational energy. Now whatever form it takes, we can call it an excitation of some sort. So some form of energy happens in the liquid, alright, so the energy is increased somehow, so we call that an excitation. And Landau's idea is that in a superfluid, for some reason, the body moving through the liquid cannot excite any excitation. And we want to try and understand how and if this is possible. Now an excitation is rather abstract at the moment, so it helps if we think of an example. A simple example might be just to think of, say, an atom of the helium. If this body hits the helium atom bounces off. And in that way, that is a kind of excitation in that it gains energy, and the body loses energy to that helium atom, so the body would slow down. And that's one example of what might happen if it experiences viscosity. So it can be a helium atom bouncing off, or, so let me call that, can be the deflecting of an atom. Just for example, or in the case of a liquid, the moving body through the liquid can also produce some kind of a vibrational wave motion going through the liquid, like a sound wave, for example. It could be an atom, or we could have a sound wave. Right. So this sound wave then would be quantized. We know that it would be quantized, and the wave packet is called a phonon. So just two possible examples of what might happen. And phonon could be another example of an excitation. So now we have two concrete examples of this. Now from what we know classically, meaning from what we know when we have a body hitting another object, it is difficult to understand why excitations are not possible or might not happen. Surely if you hit an object with another body, alright, that body has to lose energy because this object would bounce off and take away energy from it. Now, to understand why it might be possible that for some reason the body cannot actually produce excitations, right? Lose energy by producing such excitations. Landau analyzed the problem by thinking about something called the dispersion relation. Let me write that out here. Now, what's the meaning of a dispersion relation? Well, a dispersion relation is an equation that relates energy to the momentum of a particle. Okay? So, for example, in the case of an atom, the energy momentum of the atom is related by E equals to P squared over 2m, where m is the mass of the atom. Now this relation comes from half mv squared, because we know that P is mv in this case. Alright, P is mv. That's the momentum. So that's for a object with a mass m. Okay. Just call it an atom. Now, in the case of a phonon, there's also a relation between the energy and the momentum, and this relation is given by P equals to the speed of the phonon times P, the momentum. Okay, now to see how this comes about, this relation comes from combining two equations. One is the expression for energy, E equals to h bar omega. That's the formula relating phonon energy to its frequency. Now the other is the relation between momentum and wave vector. So this comes from the de Broglie's relation between wavelength and momentum. Alright? Now when you divide the two, you get E over P on one side, and on the other side you get omega over K. And that's equal to V, the velocity. So when you rearrange this and this, you get that expression for phonon. So that's the phonon dispersion relation. That's the dispersion relation for an atom. Now Landau's idea is to realize that this excitation, alright, the possibility of having an excitation, that means of a mass actually losing energy when it hits an atom, of a mass producing a phonon as it moves through the fluid, actually depends. Whether this is possible actually depends on the dispersion relation. Now the reason why that is the case is simply because of the conservation of momentum. Let's take a look at the conservation of momentum. So suppose now that we're still looking at this body and the particle. Now that particle could be an atom, it could be a phonon, or it could be something else. It can be anything, alright, just some particle. Now let's write down the momentum conservation equations and energy conservation equations for these two. And that's, well, we need some more symbols, right? So let V be the initial velocity of the mass. Now when this mass excites an excitation, meaning when this mass either hits an atom or produces a phonon. Alright, suppose that the atom or phonon or other particle gains an energy of E and a momentum of P. And this mass, on the other hand, would lose a little bit of energy and it will change direction a little bit to, let's say, V prime. Okay, so the momentum equation then would look like this. We would have the initial momentum, that would be mass of the body times the vector v. Okay, so this must be equal to the final momentum, which is mass of the body times the new velocity v prime plus the momentum of the excitation. So these are all vectors. Now, but energy must also be conserved. So let's write that down. The energy of that would be the kinetic energy, which is initially half mv squared. And after producing the excitation, the new kinetic energy of the mass is half mv prime squared. And the energy of the excitation is E. Now we let it be E. Okay. So now let's try and find a relation between the velocity of the body and the energy and momentum of the energy and momentum of the excitation. Right, the idea is to see whether there's some connection between the dispersion relation for the excitation and the velocity of the body that can, for some reason, prevent the excitation from happening. Okay. So, in the first step, let me rewrite that as, now if I move this over to the other side, I have v squared minus v prime squared. Alright, now the half m can be factored out, and I have e on the right side. Okay, if I rearrange this, alright, I'll get vector v minus vector v primed. Just move that over there. And I can factor out the m again. That's equal to momentum p. Alright. Now, from here, I can factorize that now move these over to the right, so it's 2e over m on the right. Then I'll rearrange this so that I get v vector minus v prime vector. Okay, with the m moved over to the other side. Like that. So I have these two equations. Alright, so fairly straightforward. Now the next thing I'm going to do is this. I'm going to simplify. First, I'm going to simplify that equation. I'll call that equation 1 and I'll call that equation 2. Okay, let me simplify that. Now, equation 1, the v plus v primed here refers to the initial velocity plus the final velocity. Now, we are thinking of the mass of an object, okay, which is a lot bigger than, say, the mass of an atom, or has energy which is a lot bigger than that of a photon. Okay, so this means that after producing the excitation, the new velocity is only slightly different from the old one. Okay, meaning the v and the v primed are very nearly equal. Right, v is very nearly equal to v primed. So we can say approximately that v plus v prime is approximately just 2v. So this is approximately true from 1. Rewriting it like that. Now then, for equation 2, we are going to consider taking the magnitudes on the two sides. Okay. So if I take the magnitude of p vector, I just call it p over m. Now let's look at this expression there. Now the two v vectors, if I draw the vectors, might look like that. So that's the starting v direction, and that's the direction after producing the excitation. So in general, it can be in a slightly different direction, and it can have a slightly different magnitude. Just draw that. And the v minus v prime vector would be that. V minus v prime. So that's that. So that's my p over m. Now according to this picture, okay, you can see that the length of this, alright, imagine for a given v and for a given length of v and a given length of v primed. This, the length of this part, which is this, the length of this must always be less than the length of the difference in length between those two. Let me write that down. So the length of this side must always be it must always be more than. It can be more than or equal to the difference between those two lengths. Now to see why this is so, let's just, well, we would expect that v prime, the length of v prime is a little bit shorter than the starting v, because you would have lost some energy. So this might be a little bit shorter. So to understand this, let's draw some pictures. Okay. So let me draw this again. Now, so this, I'll exaggerate it a bit now. This v prime is a bit shorter than this V here. So what we are going to suppose that we are going to consider what happens for, say, a particular V and a particular V prime. So the length, we suppose that the length don't change for the moment, but we are going to move the angle between them around and see what happens to this length, alright, which is the difference between the two vectors. What happens to this length? Okay, as I say, I fix that, but I move this vector up and down by changing the angle. So if I move this up and down, surely this length changes. So if I move it further up, if I move this vector upwards by increasing this angle, this length increases. Okay, if I move this vector down until it is along this line, this length would decrease. Okay, so when this is exactly along this line, that means that's V, this is V, but V prime is now pointing along this direction, then this distance is just here, just that distance. We can see that it would be at its shortest when V prime is along V. But if I move V prime up like that, this distance would increase. So whether it's this or this, alright, they are both given by that expression there. Okay, so that means that this distance must always be more than this distance, and this distance is simply V minus V prime, which is that. Okay, so now we understand why that's the case. Let's make use of this inequality here. So this is just the same as P over M. I'll call that 3. So that's just P over M. It must be more than or equal to V minus V primed. But we know V minus V prime from here. We have that there. Okay, and I can make an expression for that. I can make that the subject if I move 2V over to the other side. So this is 2E over M. If I can cancel the 2, just bring the V over, and I get E over Vm. Okay, and now I can cancel the M. Now I want to make V the subject. Okay, I'm interested in V because that's the velocity of the body moving through the fluid. So I bring V up over to the other side. I bring P down here. Right? So now I have an inequality. Now this inequality tells me something interesting. That V cannot be smaller than E over P. What does this mean? Well, it means that if the body moving through the liquid, so let's imagine the body again, you have a body there, moves through a fluid. If this body moves at a velocity which is less than E over P, what happens? What does it mean by V must be more than E over P? Well, if you recall what we did initially, we wrote down the momentum equations for the body creating an excitation. That means either knocking away an atom or producing a phonon. Okay, so in a sense that was our starting assumption. Right? We assumed that an excitation was produced and we arrived at this inequality, that V must be more than or equal to E over P, where E is the energy and momentum of P, the momentum of the excitation. So in other words, the assumption was that an excitation will be produced. Okay, and if you assume that excitation will be produced, we get this result. So if this result is not true, that means if V is, so here, this one, okay, it comes from assuming that excitation is produced. Now, but if, so conversely, if V is less than E over P, it means that excitation is not produced. That's what it should mean. Now, at this point, it's getting a little bit abstract. Okay, so we'll try to understand that a bit more in a moment. But let's just take this a bit further and think about what it means if an excitation cannot be produced. This means that as the body moves through the liquid, for some reason, let's say for some reason, okay, it cannot produce any excitation. That means it cannot deflect, knock away an atom, or any atom, or it cannot produce any phonon. So it cannot produce any excitation. It cannot give its energy to make something else happen. So if that's the case, that means that the body cannot lose energy. And if the body cannot lose energy, that means that it will just keep going and going. It will not slow down. And then we have our superfluid. Okay, so in other words, we reach this conclusion. Okay, excitation cannot be produced. Alright, this implies that there is zero viscosity. And this in turn implies that we have a superfluid. Okay, so potentially this can give us an explanation of why a superfluid is possible, because excitation cannot be produced. Now let's go back and look at what this means, how this is possible. Okay, because this part is getting a little bit abstract. Surely, if the body hits an atom, it has to be able to lose energy to it by knocking that atom away. Well, so let's then take a look at what it means in terms of the dispersion relation of the atom. So is this ever possible? Is it possible that V is ever less than E over P if we think of the mass hitting a small particle like an atom? Okay, when it hits the atom and the atom bounces off with energy E and momentum P. Is it really possible that for some reason the body, after hitting the atom, does not lose any energy to it? It seems unlikely. Okay, but let's check this carefully. Now, how do we check this? Right. Let's think in terms of E over P of the atom. For the atom, E is related to P by P squared over 2m, as we have seen. That's the kinetic energy term. So let's sketch a graph. Okay, so once again, we need to do some graph sketching. And we know what that looks like. It's a P squared graph, so it's a quadratic graph that we know. Quadratic curve. And think about E over P. on the graph. What does it mean? So E and P would be a point on the graph. Okay, it has to satisfy this equation. And E over P, we can think of E over P as this distance, that's the E, divided by this distance, which is the P. So in other words, E over P is the gradient of this straight line joining the origin to that point, the point given by P and E. So it's that gradient. Now as we move this point, you can imagine we can consider different points on this curve. Alright, and doing that is like moving the point up and down along the curve. If you move the point up and down, the line joining the points to the origin also changes in gradient. So we can move it down here or move it up there. Now since this is an inequality here where we are wondering what happens when or whether V can ever be less than E over P, let's try and move this so that we make E over P as small as possible. Let's try and find a smallest value for P. So as we move this point down, the gradient of the line gets smaller and smaller. When this point reaches here, clearly the gradient is horizontal. In other words, as far as this atom is concerned, the minimum E over P, meaning this gradient, is equal to 0. And now, if we now look at this equation, can V ever be less than E over P? Now, when we think about this, whether this can ever happen, we have to think about the smallest possible E over P. Okay, because if you think of just any E over P, that, for example, E over P of this, okay, it is possible to have a V smaller than this gradient. Okay, but then you can always find another E over P which is smaller than that velocity. And then perhaps the smaller E over P can be excited. Okay, so in order to consider this possibility, we have to see whether there is what the smallest possible E over P is given this dispersion relation. And in this dispersion relation, the smallest possible E over P is 0. So that means that if we want V to be always smaller than any E over P, we must consider whether V is less than 0 in this case, whether this is possible. Well, now let's think about the V. The V here is the magnitude, you must remember, of the initial velocity of the body. It's the magnitude of this body. So a magnitude cannot be less than 0, which is what this inequality is saying. So this is impossible. Okay, it's just not possible. So it means that given this dispersion relation, for say just an atom on its own in free space, when the mass hits the atom, it must always lose some energy to it. Okay, so the mass would slow down if it keeps hitting lots of atoms along the way. So if you have lots of atoms in free space, like in a gas, for example, the atoms would always lose its energy to the gas as it moves through it and experience viscosity. Okay, so it's not possible that the particle does not produce any excitation in this case. So this is not something new. This is what we expect. So we are still not moving very far yet in terms of understanding superfluid. Now, but this is not the only dispersion relation that we have. We have another dispersion relation that's quite different. We have the phonon dispersion relation, which is energy is equal to velocity times p, that we've seen just now. So when a body, mass m, moves through a fluid, can it produce a phonon with some E over P and then lose some energy and change direction? Can this happen? So according to the inequality which we observed just now, the velocity, for this to happen, the velocity must always be more than or equal to all possible E over P of the phonon. Otherwise, excitation can't happen. Now let's look at E over P for that. Now that's a simple equation. We can just rearrange that. In the case of the phonon, E over P is just V of the phonon. Now that's going to be confused with this V here, so let me change this to a more commonly used form. We'll call the V that, replace that V by the letter C. Okay, that's confusing. So E equals to Cp. Now use C in this case for the speed of sound in the liquid. Now that's not a commonly used symbol in other parts of physics. We normally take C to be the speed of light. But in considering phonons, right, we would sometimes also use C to represent the speed of sound. So we have to be a bit careful with this use here. So let me call this C. So V is more than or equal to C, which is the speed of sound. So that means that for this excitation to happen, V must be more than the speed of sound, which is a fixed number, so it's easier to remember what E over P means in this case. So if V must be more than or equal to the speed of sound to excite the phonon, just means that if V is less than the speed of sound, then no phonons are excited. And now we have a very simple conclusion. If V is less than the speed of sound, there can be no losing of energy of the mass. And this means that the mass can just move through the liquid without losing energy and without experiencing any viscosity. Alright, all this is of course assuming that phonons are the only kind of excitations possible in a liquid. But in reality, liquids may have other kinds of possible excitations. But this possibility, right, this possibility that we can have a dispersion relation that prevents excitation from happening, like in this example, this possibility is important in leading to ideas that explain superfluids. So perhaps in a superfluid helium-4, is it possible that the types of excitations that are present in superfluid helium. Excitations like phonons, or maybe others that we don't know. Is it possible that the dispersion relations of those are somehow is it possible that they somehow have dispersion relations that makes it possible, if the velocity is small enough, that no excitations can happen? Now, so this means that in order to find out whether this is the case, we need to know what are the types of excitations that are possible in superfluid helium. Now, there is a way to do that. From the Debye model, from what we have learned about phonons, we know that phonons are related to heat capacity. For example, in a solid, we know that if we plot, say, the heat capacity against temperature, phonon contribute a heat capacity which is related to T cubed, as we've learned in the Debye model. Now, in the case of superfluid helium, the heat capacity has been measured. Now, in this case, let's imagine plotting a log graph. Okay, so Kelvin. So this might be, say, 1. This might be 0.1. So that's a log graph as well. So if we plot the log graph, maybe 1, 10, and so on, then it was found that we get a straight line with a gradient of 3. So this, in other words, this goes as T cubed. Okay. Now, that's the result of measuring the heat capacity of liquid helium at very low temperatures. So what this means is that for superfluid helium, actually, at very low temperatures, the contribution to the heat capacity is actually phonons, even though it's a liquid. Alright, we have previously learned about phonons in a solid, but it turns out that phonons is actually the only excitation which is present in liquid helium at extremely low temperatures. But as it turns out, it is not the only phonon that is present in superfluid helium. Now, superfluid, we know, happens below about 2.2 Kelvin. Now, round about 1 Kelvin, it was found that the slope of this graph changes, so that here, down here, is no longer T cubed. And what this means is that at slightly higher temperature, where it's still superfluid, it must mean that there are new excitations which are not just phonons. There must be something different happening here. Now, what Landau did was, he proposed that there is a new kind of excitation, alright, whereas you have phonons here. He proposed that there's a new kind of excitation leading to this change in behavior called rotons. Okay, and what he did was, he postulated a new dispersion relation for rotons. Okay, let me draw that. So dispersion relation for phonons, we know, is a straight line. That's the E equals to Cp with the slope C. So this is the phonon dispersion relation. Now, Landau postulated a roton dispersion relation that looks like a parabola, and that's situated somewhere here. Now, the reason why he made this up in such a strange place is because he found that with this dispersion relation, he was able to derive the heat capacity. That a heat capacity formula that agrees with this measured heat capacity. Now, if you remember from what we learned about phonons in solid, when we calculated the heat capacity from the phonon density of states and phonon distribution, we had to make use of the dispersion relation. Well, we did not call it the dispersion relation then. We made use of this energy equals to h bar omega, and we made use of the relation between omega and wave vector and the velocity of the phonon. We had to make use of this when we calculated the T cubed heat capacity of phonons. So by changing these relations, at higher temperatures, Landau showed that if there is a new dispersion relation that looks like a parabola, the energy calculation and the heat capacity calculation will actually lead to a formula that agrees with this measured heat capacity. So combining this line and this parabola, Landau postulated that the liquid helium heat capacity looks like this. Right, so this really weird looking graph is postulated by Landau, and he actually obtained quantitative results for the graph, estimates of the graph, by fitting this part, using this part to get a formula for the heat capacity and then adjusting this so that the result agrees with the measured heat capacity. So he have a quantitative graph with actual numbers and so on. And based on this graph, he made use of his relation, which is this one, that V must be more than the lowest possible E over P. Now we can, with our understanding so far, right, we know that the way to make use of this inequality is that we have to think about the lowest possible E over P in the dispersion relation. So I use the word subscript minimum here. Okay, as long as there is an E over P that is still possible, all right, for the given velocity, then the excitation can happen. So that's why we look at the minimum. So if we look at this graph, we want to see what the minimum E over P is. Now if I think about any point in the graph, for example, then as before, think about the E over P as the gradient of a straight line joining the origin to that point. And think about this slope as you move this point around, or as you consider different points in the graph, and look for the place where the slope is the smallest. Now clearly, that point is somewhere here. Alright, if you move to any other point, you'll get a bigger gradient. So this gradient gives us the smallest E over P. Now the important thing about this gradient is that it is not zero. Okay, because there is a slope. So, and if it's not zero, that means that V must be bigger than a non-zero value, so that it can produce these excitations, which in this case can be phonons or rotons. And as long as V is smaller than this value, right, it can't produce any excitations and it will act like a superfluid. And Landau, even with his curve, was able to estimate a value for this, and was found that this is about 50 meters per second. Right, a very definite number that it can in principle be checked by experiments. And indeed, he postulated that in the years in the 1940s. And indeed, after about 30 years or so, this was indeed verified by an experiment in which an object is very small object is moved through a superfluid, and it was found that there's no viscosity until the object exceeds this 50 meters per second, whereupon there is a sudden increase in resistance to the object. So, okay, I think that completes our discussion of this topic, and I'll just finish off by giving this minimum value a name. This is the minimum, or rather this minimum E over P is actually the maximum velocity. Okay, VL. Right, this is the biggest velocity for which superfluid is still possible. Alright, zero viscosity is still possible, and it has a name. Just realized that I've not seen much of the writing. Let me move this up. Sorry about that. Hope you have not missed much. Now, so that I was saying, the V must be more than a minimum value of E over P, and the minimum value was found by looking at this part of the graph, okay, and estimated by Landau to be 50 meters per second. Okay, so I said that this minimum value is given a name, and the name of this value is the Landau critical velocity. So that completes this topic on Landau's explanation for the superfluid. We'll stop here.